discuss XML processing on the cluster, bringing XQuery 3.1 to RumbleDB. So let's get started. So we, as experts, are very familiar with the XML data model. And we all know that we can use the XQuery declarative language to query collections of XML documents. But if we take a bird's eye view when dealing with
base from the Hadoop ecosystem or object storage provided by cloud vendors, the core question then becomes, how can we efficiently query a large collection of XML data with millions of items distributed on a cluster? Traditional query engines are simply not designed to efficiently perform this task. Well, our solution to this challenge is RumbleDB, a query engine developed as a research effort at the systems group at ETH Zurich. If we take a closer look at its definition, RumbleDB is defined as a query execution engine for massive datasets. When we say massive datasets, we mean the millions of files and the petabyte size of the use case we just described. Moreover, RumbleDB is a query execution engine for semi-structured heterogeneous datasets, which encompasses any type of data found in the modern lakehouse, supporting different formats like JSON, XML, CSV, and various storage mediums as well, ranging from HDFS and S3 to even the local disk. Moreover, RumbleDB provides native JSONiq and XQuery 3.1 support. JSONiq here is a declarative query language developed aside RumbleDB with a JSON-friendly syntax and still very close to XQuery. Here, I really want to focus on the fact that RumbleDB supports XQuery 3.1 and XML natively. This native integration occurs at two critical levels. First, at the query level, we utilize a dedicated FLWOR parser specifically for XQuery. And second, at the data retrieval level, we access and parse XML data directly from the storage medium. Both of these aspects allow us to benefit from great performance when dealing with XML and XQuery workloads. In terms of feature support, RumbleDB supports a wide range of XQuery 3.1 expressions, which cover fundamental aspects of the standard. Our support includes arithmetic operations and comparisons, FLWOR and control expressions, node constructors and comparisons, whose support has been recently introduced, path expressions, and XPath and XQuery functions. We also support extensions to the standard, including the XQuery scripting extension proposal, which was developed starting from a working group note and providing scripting capabilities and support for statements within the language, and the JSONiq update facility, which is based on the XQuery update facility version 1.0, adding updating expressions to the language. In terms of compliance, the authoritative test suite for verifying how much a query engine is compliant with the XQuery 3.1 standard is the QT3 Test Suite, which provides more than 32,000 tests testing various aspects of XPath and XQuery 3.1 features. As part of our development workflow, we automatically evaluate RumbleDB on the test suite and collect results in our continuous integration pipelines available publicly on our GitHub repository. Specifically, RumbleDB 2.0.0, codenamed Lemon Ironwood, show promising results in terms of coverage of the QT3 test suite. As we can see in this graph, we currently cover more than 50% of the test cases. Most importantly, as we can see here instead, thanks to recent updates to the XQuery parser, less than 5% of the test failures are due to parsing exceptions. The majority of failures is instead related to unsupported features and functions, which show how RumbleDB's support of XQuery is almost complete at the parsing level, and the engine is actually ready to support even more features than what it currently does. But coming back to our definition here, RumbleDB's true novelty in the space lies in its ability to run both locally, like traditional query engines, and distributed on a cluster with a high degree of parallelism. So let's now examine what happens when we run a query in RumbleDB. Consider this simple query that iterates over XML files and returns the ISBN of each book. We issue this query from a single machine here. RumbleDB can then send the query over to a cluster of machines. And in a distributed environment, the cluster nodes first retrieve the XML data, and each single node then accesses the data from the storage medium, for example, HDFS or S3, enabling parallel processing. The analysis, in this case extracting the ISBN number, is performed in parallel across the cluster. The results are then returned to the initiating machine, and in this case, they're simply outputted on screen. So, how does RumbleDB achieve this distributed and parallel processing of queries? The secret relies on the fact that RumbleDB is backed by Apache Spark, which is a popular and robust framework for distributed computing. Let's now dive deeper on how we're able to leverage Spark in RumbleDB. But first, let's introduce some core Spark concepts, so we make sure we are all on the same page. The fundamental logical abstraction within Apache Spark framework is the RDD, or Resilient Distributed Dataset. RDDs are characterized as being big collections of data that by nature are partitioned and distributed over a cluster of nodes. The life cycle of an RDD follows three distinct phases. First of all, an RDD needs to be created. The creation of an RDD happens starting from any data that can sit on object storage, distributed storage, the local disk, or even created on the fly from the Spark Python or Java APIs. The data then goes through several core transformations which take as input an RDD and produce a new RDD. Transformations basically reshape the RDD from one form to another, applying operations like filtering or sorting, and so on. Transformations can be chained arbitrarily, allowing to perform complex data manipulations on RDDs. Finally, there is what is called an action. The role of an action is to output an RDD on a medium such as object storage, distributed file systems, or, as in the most basic use case, on screen directly. And here we have seen a linear lifecycle for a single RDD. But the same approach generalizes to any directed acyclic graph. Transformations can be used to combine several RDDs together coming from different sources or chained with other transformations. And as we can see, the Spark processing model is extremely flexible and powerful. But with great power also comes a potential performance costs. And this is when another very important feature of Spark comes into play: lazy evaluation. Lazy evaluation means that only when an action, like outputting an RDD on screen, is added, the transformations in the DAG sitting on the critical path for that action are actually processed. And this feature is extremely important for performance and efficiency, as it allows processing the transformations only when they are needed. So now the question is, how can we leverage the distributed processing model of Spark in our query engine, RumbleDB? Well, in the end, our job is simple. Our main job in RumbleDB is to map declarative queries from XQuery and JSONiq to Spark transformations and actions. For example, let's consider the XQuery workload we showed before that reads a list of books and extracts their ISBN. Let's now break down a possible execution of the query in RumbleDB. Here I will abstract some details for the purpose of this talk, but the core concept stays the same. First, we need to fetch the XML files. We use the spark.read.text API to fetch the data from the data storage medium. The result from this operation is an RDD of strings, each of them corresponding to an XML document. Next step, we proceed to actually parse the XML data, applying a map transformation to the RDD. We pass an XML parsing function which results into another RDD containing the parsed XML trees we can use for further processing. Then we need to extract the ESBN from each document, so we apply another map function, this time a forward access step that extracts the property from each of the XML trees. The result is an RDD of strings, the ESBNs extracted from each document. Finally, we just return the ESBNs. In this case, we want the result to be output on screen, so we apply the collect action to the Spark RDD. From this breakdown, we can appreciate how elegantly a declarative query can be mapped to a set of Spark transformations. And let's remember that this is a logical view of the query execution plan. What happens under the hood with Spark is much more complex than this. First, these RDDs are never processed as discrete steps in the cluster. None of these RDDs actually exist in memory completely at any given point in time. From the creation of the RDD, from the data source to the final output action, there's a continuous flow of tuples, each of them moving from one transformation to the next one. And most importantly, this view of the query execution plan here elegantly hides the fact that each of these transformations and RDDs are actually distributed on a cluster. This is the nature of the Spark execution model. With this example in mind, let's now take a closer look at different types of transformations and their performance implications. If we consider the call to the map access step function here, there's no implied ordering or uniqueness constraint on the result. This means that we can perform the forward step on each tuple independently from the other ones. Transformations like map functions can run completely in parallel on all the nodes of the cluster, achieving full parallelism, and it's actually very efficient. But this is not always the case. Let's consider, for example, adding an order by clause to our query, sorting the books ascending by publication year before extracting the ESBN. Such clause is mapped to a Spark sort transformation. And transformations like sort that introduce global ordering and uniqueness constraints require shuffling tuples around the cluster in order to be computed. But what is shuffling? Shuffling means moving partition of RDDs across nodes in the cluster. This operation is expensive because it corresponds to, first, network operations, because we actually need to move the data from one node to the other one, generating traffic in the cluster network. And second, serialization and deserialization costs, because every single time we need to transfer data around, we first serialize the memory representation into bits for transmissions at the sending node, and then at the receiving node, we need to deserialize it back into the memory representation to continue processing. When shuffling is required, all nodes need to receive all partitions of an RDD in order to complete processing, which means that in general, shuffling has a quadratic complexity relative to the number of nodes in the cluster. So we can clearly see how it is very important for distributed Apache Spark applications to reduce the number of shuffles performed during execution. In the case of the implementation of XQuery in RumbleDB, we can clearly distinguish between shuffling and non-shuffling expressions. Expressions that do not require shuffling transformations include for, let, where, arithmetic, conditionals, and more. All of these expressions can achieve full parallelism so they are very efficient on the cluster. Whereas expressions that do require shuffling due to ordering and uniqueness constraints include group by, order by, uniqueness checks like distinct values, and path expressions. So, in order to increase the efficiency of RumbleDB, we need to focus on reducing shuffling on expressions that require them. In our initial implementation of path expressions, we would run at every single step both a uniqueness check implemented with the distinct transformation and path-based sorting implemented with the sort transformation. These cause 2 shuffles for each step in the path expression, resulting in a very inefficient execution. We can do better than that. First, we focus on how we could reduce the impact of existing shuffles. For example, we can reduce the cost of serialization and deserialization. We notice in this case that when an expression contains only forward steps, any information about the parent nodes is irrelevant. The expression focuses on the current and child nodes in the XML tree. This means that in this case, during shuffling, we can skip the serialization of parent nodes altogether, resulting in less data being transmitted over the network. Very interestingly, this optimization can be performed completely with static analysis of the path expressions in the submitted query. With the second optimization instead, we redesigned the uniqueness and sorting mechanism. We first perform the sorting by grouping the tuples by document, which is mapped to a group by transformation. After the grouping, the resulting RDD would be partitioned by document across the cluster, which means that we can then apply uniqueness and sorting constraints within each document, and such transformations will be applied locally within each partition sitting on a single node and without any additional shuffling required. Overall, with this approach, we are now able to perform just one shuffle while maintaining the desired guarantees on the query result. We also worked on more experimental challenges. For example, if while processing a path expression, parent pointers are removed, so optimization number 1 is applied, and the right-hand side of an XQuery expression is a forward step operation, so it just goes down the tree, then we know with a high degree of certainty that we can skip uniqueness checks and sorting completely, eliminating the need of any shuffling. Of course, there is much more complexity involved to determine when skipping sorting and uniqueness checks is sound. We cannot guarantee the correctness of the results in all situations, so this feature is disabled by default and can be enabled with the flag by the user. Anyway, with this experimental feature, we wanted to try to explore the full potential of applying such optimization. A lot of effort has been spent in implementing RumbleDB under the assumption that running queries distributedly on a cluster is a good idea. But does actually parallel querying pay off in the end? Well, it turns out it actually does. In a benchmark earlier this year, we compared the performance of the popular Saxon query engine compared to RumbleDB 1.23, running on a powerful 4-node cluster hosted on AWS. We ran the same XQuery workload on both engines, measuring the runtime of each execution, and we gradually increased the size of the datasets from 64 to 16K documents. Our results show that with smaller datasets, Saxon performs better than RumbleDB, as such query engine is highly optimized for running on a single machine and benefits from years of development and experience in the field. However, as the dataset size grows, the runtime of queries run with Saxon rapidly increases. Already with a dataset of around 1K documents, RumbleDB is able to execute the query faster than Saxon. But results of our research are much more clearer when we start to look at queries with 4K documents. Here, RumbleDB achieves a 2.5x speedup compared to Saxon. Furthermore, if we enable the experimental optimizations discussed before, we achieve a stunning 7x speedup. And with larger and larger data sets, we imagine the runtime difference to grow even more drastically. So, in conclusion, with our research, we clearly showed that querying massive datasets on a cluster is possible and is actually efficient. We have just scratched the surface of what is possible with RumbleDB, and a long journey is ahead for this project. So the question now is, what's next? If we take a look back at the coverage of the QT3 Test Suite, RumbleDB is in a good spot in terms of support of XQuery 3.1, but there's still a lot to be done here and a lot of features that can be improved and added. We foresee future work to focus on implementing more core XQuery features. Specifically, this includes XQuery data model features, XML related functions, and even more node constructors. Then we want to optimize, and optimize. Our goal is to close the gap between RumbleDB and existing engines, even when running on a single node. This means lowering the point where existing query engines are more efficient than what RumbleDB currently provides. Just imagine a query engine with the massive parallelism of RumbleDB and the blazing local performance of Saxon. That is the future that we are aiming for. We are genuinely excited to bring to the XML community the new features and improvements we discussed today as part of RumbleDB 2.0.0, codenamed Lemon Ironwood, which is now available to the public. So, if now you're wondering, what can I do next? We have made it really easy for you to get started. And there are 3 simple ways to jump in. First, you can start using RumbleDB right away. Just integrate RumbleDB into your Python workflow by running pip install JSONiq. That's it. From there, you can write XQuery and JSONiq queries over your datasets directly in your scripts. Second, if you like to try things out without installing anything, we set up a Google Colab sandbox where you can experiment with all the RumbleDB features directly in your browser and instantly. And third, we'd love for you to get involved in the community. You can visit our GitHub repository at github.com/rumbledb/rumble and our official website at rumbledb.org. We really welcome your feedback and ideas on how to bring this project forward. With these resources, you can start exploring RumbleDB and the power of distributed XQuery today. Thank you so much for your attention, and I hope you will have a great continuation of the conference.
Some benchmark against basics.
Okay.
Or
now we can hear.
Okay, so I will repeat it. Okay, so first I thank for your very interesting presentation. I'm always amazed what you are doing with query languages in Zurich. And I just wanted to ask if I get it correctly that for each query you have to parse the XML documents and then evaluate the query against the freshly parsed data. So there are no indexes. Is that right, or I misunderstood how the query is being executed?
So there's no indexing. Thank you so much for the question. First of all, there's no indexing involved because like the way that you get like the data, like you store the data, you have to imagine the lakehouse pattern. So the data is stored directly in their native form, which can be XML in this case, but of course we support also like JSON, CSV, and so on. So there's no real indexing or any type of ETL form of transformation of data. And so the data is basically, the query runs on the data as they're stored, and it fetches the data, and then you directly operate on the document itself, in this case XML.
Maybe I can add also that there are 2 different paradigms in database systems. There is the paradigm where you have a proprietary format optimized with indices, UETL, so a typical database systems like the standard relational database systems like document stores like MongoDB. And then you have the data lake, which is you just throw your data onto a distributed system, and then you just you just do it without indices. You just read the data, typically for aggregation and so on, and it's highly optimized for reading. But we are now observing a convergence of the two, that there are attempts more and more to make it converge again and bring back faster speeds on the data lakehouse. So in the future, it is possible that we can extend the system with indices when it will start to be done more commonly on data lake. So this is what's called the lakehouse paradigm, this idea of bringing back desirable properties of the classical systems to data lakes, including updates, for example.
Any other questions on Zoom, maybe? I'd like to ask Norm if he's going to hire Matteo to fix his application.
Not sure I'd have gone so far as to say fix, but nice work, guys. Nice work.
Thank you.
Yes, there is a question from Adam.
Hi guys, thanks. That's really interesting. I just wanted to ask about how the data is distributed in the cluster. Is it sharded, or is it like every node has a full replica? Thank you.
Okay, thanks for the question. Well, how the data is distributed on the cluster, it really depends on the storage layer you're using. Like the cool thing about RumbleDB is that we are a query engine, and Spark itself is a distributed processing framework that doesn't have anything related to the way that you store the data on the cluster. It really depends on the technology you're using. RumbleDB works with even the local disk, so you can run it on a single machine. And of course, the data sits on a single machine. Or you can run it, for example, with HDFS. And in that case, if you pair a Spark cluster with an HDFS cluster, where the data is basically distributed on a cluster, and it has also like some replicas in the cluster itself, then you get the power of the distributed processing. And as well, we support object storage, which is, again, another different paradigm for storing the data. And in that case, you benefit from having a cluster because you can interact with the object storage provider in the cloud with multiple machines. So you potentially have more bandwidth to interact with these systems. But really, like, we abstract away, RumbleDB abstracts away from the way that data is partitioned or sharded in the cluster, because we just access the data, let's say.
There's one last question by O'Neill.
Yeah, hi. Yes, thank you very much for this talk. Just a quick question on the results, or what you had on the graph there. Is there anything you can say about the structure of the documents? Did you try different sorts of structures, which might give different results depending on if it's document centric or data centric, that sort of thing?
Yeah, okay. So on the details on that evaluation, it's a previous work that has been done by my predecessor, Marco Schöb, and I will share with you like the link to his master thesis, which is available publicly. So you're going to have all the details on that. I don't know if maybe Dr. Forni has a little bit of more insights in there, can answer the question.
Thank you very much. Gisela, you want to say something? Sorry.
Yes, I can maybe give a complement of answers. So typically in the most classical setups that you can imagine in such systems like that data lakes, but maybe also document stores, we have huge collections of rather small documents. So as a ballpark, you can have millions or billions of documents, or even trillions if you have huge clusters. But the documents typically would be up to 10, 16 megabytes. Some systems even have a hard stop. RumbleDB doesn't have a hard stop, but typically a single document would be 10 or 16 megabytes. This is usually how it's done on the JSON side. XML, maybe there's more habits to have larger documents. I feel in XML, and then you can use other kinds of techniques to read it more efficiently. But that we haven't tested it yet. So the structure was pretty simple with huge numbers of small documents. I also wanted to give a complement answer to the previous questions on the storage layer. It's a very important thing. To give a bit of background why there is Hadoop and the Hadoop distributed file system is that if all your data is stored on a single machine, even if you have plenty of cores, and RumbleDB can have multiple cores thanks to Spark, you're still limited by the speed at which you can read from the disk. You have a bottleneck on the read I/O from the disk. And so what happens when you move to a data lake like S3 or HDFS is that you shard your data. So it's distributed all over the cluster in blocks. Roughly the size is 128 megabytes. And they are replicated 3 times each by default and distributed all over the cluster. So then you parallelize reading from the disk. And this is why you get a massive increase on speed because of the parallelism. Now S3, the reason it's different from HDFS is that in HDFS, it's stored on the same machines. So it's local reads. You're locally reading from the disk on every machine. S3 would be a remote read because the machines on which the objects would be stored would be different machines. But if it's collocated in the same cluster, then this can be quite fast as well.